camera or something.
Okay, you're live.
Hello and welcome to another live session for Astronomy State of the Art. If I look a little garish, it seems to be because our levels are a little weird on the camera, so I'm kind of washed out. I'm not usually that glary, but anyway, floor is open for questions on any aspect of astronomy. As you may have noticed, if you've checked in on the website recently, our enrollment is up at about 23,500, making us by far the largest astronomy MOOC and one of the largest MOOCs around. So I hope that's generating some questions today.
We do have some questions ready to go, and so here's our first question from Irene. Why are there still photons all around us from the cosmic microwave, or from the cosmic background radiation? My sense is that once they were emitted shortly after the Big Bang, they wouldn't still be present 13 billion years later.
Okay, that's a great question, because it is a little counterintuitive that radiation from an event that took place 13.8 billion years ago would still be present. So I think the way to think about it is think of the universe as a single entity, a container of space and time. Now, the trick there is, of course, to not imagine it, therefore, as something like a sphere or a balloon filled with space and time, and galaxies in the middle of it are expanding or moving apart. Because in practice, the universe doesn't have to have an edge. So we can think of it as a sort of boundless situation of time and space. However, the distance between any 2 points in that space has increased dramatically since the Big Bang. So in the first stages of this situation, the temperature is very hot because the density was very high. And that radiation at the time of the Big Bang, or at the very instant of the Big Bang and thereafterwards, would have corresponded to intense gamma rays, extremely high energy radiation. In the Big Bang model, the temperature of the radiation that essentially permeates and fills the universe is very simply related to the size of the universe, or the distance between any 2 points as the universe expands. It goes inversely as that. So as the universe gets 10 times larger, for example, the temperature of that radiation that fills the universe gets 10 times smaller. It's a really simple piece of thermodynamics, actually. The microwave background radiation that we see in those maps, those beautiful maps made by the satellites WMAP and now Planck, represents a time when the universe was about 1,000 times smaller than it is now. So at that time, the radiation that filled the universe had the wavelength or frequency of dull red photons, just slightly longer wavelength than the eye could see. But again, that radiation filled the universe. So part of the answer to the question is, throughout this scenario, from the Big Bang onwards, this radiation was ever present. It was sort of omnipresent through space, filling every available square centimeter, cubic centimeter of space-time. And as the universe expanded, the photons were stretched, literally by the stretching of space itself, to longer wavelengths, lower energies, and lower temperatures. So that radiation that we see in those beautiful microwave images with a temperature of about 3,000 Kelvin, which would correspond for thermal radiation to dull red photons, has stretched by a factor of 1,000 since then. The universe is now 1,000 times bigger, and therefore the volume is 1 billion times larger. And that radiation is now at a temperature of 3 degrees Kelvin, which corresponds to microwave radiation, very dim, low intensity electromagnetic radiation. But it's still there. So those photons have been in the universe throughout that 13.8 billion years, traveling at the speed of light, 300,000 kilometers per second, wherever they're going, from A to B or in whatever direction they're going. And in fact, these photons are traveling in all different directions, every different direction, just permeating space, traveling at the speed of light as they should. And now, 13.8 billion years later, long after the Big Bang, those photons are still omnipresent, still permeating space, but they've receded or been stretched in wavelength to almost be imperceptible. The intensity, or the radiation intensity, of the microwave background is very dull now because of that expansion. To put a number on it, in any volume of space, the radiation intensity of the microwave radiation is about 10 to the minus 5 watts. That's 100,000th of a light bulb. So it's really very, very dim radiation in microwaves, but it is still there. It's in the room you're sitting in, it's in your house, it's in the solar system, it's in the Milky Way, it's in the spaces between galaxies. It is essentially everywhere. And radio telescopes on Earth first detected this radiation almost 50 years ago, and now we, of course, study it in exquisite detail with satellites. But it's a very good question because it gets to the heart of an issue of the Big Bang, which is this radiation permeating space, equal intensity in almost every direction to a tiny fraction of a percent, was essentially the clinching evidence that the Big Bang idea was correct, because it's extremely difficult to hypothesize any other reason why space would be filled with microwaves of almost uniform intensity in every direction with a temperature of 3 Kelvin.
Okay, so our next question is from Stanley, and he has an exoplanet question. Are planets like Kepler 186f close enough to do atmospheric spectroscopy during a transit?
Yeah, good question. It's one of the big challenges of exoplanet research following up these new targets that have emerged. Just as an aside, if you like to keep up on this stuff, I was on JPL's exoplanet website this morning. I actually tweeted about this just this morning. And the planet counter, of which includes all the candidates, but these candidates are known to have very high probability of being real, but the false detection rate is extremely low. But the planet counter clicked over 5,000 for the first time. And remember, it is barely 20 years since the first exoplanet was detected. And now we know 5,000 of them, which is an extraordinary rate of progress. So to your question, the question alludes to going beyond just increasing the body count of exoplanets, which now is not that hard to do, even though Kepler is diminished in its capabilities, and learning more about them, and in particular, learning about their atmospheres. That's the heart of the search for life in the universe, is the search for an exoplanet whose atmosphere has been altered, we think, by microbial metabolism at work. That's sort of the holy grail of exobiology right now. It will be the detection of life elsewhere in the universe, we think, unless, of course, one of the Mars missions gets successful and finds microbes under the Martian surface. I actually think the exoplanet hunt for life will succeed first. The Kepler targets are challenging, and Kepler 186 F is one of the better Kepler targets, but most Kepler targets, because they're faint stars, are fairly, and a small region of sky, are fairly far away. The typical distance of a Kepler target is a few hundred to 1,000 light years. That's really quite distance. I can't remember off the top of my head the distance to 186F, but I think it's one of the closer Kepler planets, exoplanets, probably 100 to 150 light years. So that's relatively nearby for a Kepler exoplanet. And it does put it in a good category for following up with the technique the questioner was talking about. What is that technique? It involves doing very careful spectroscopy during a transit and essentially looking for the light from the star. So remember, in a transit, the exoplanet passes in front of its star, its parent star, dimming the light of that star briefly and momentarily. And that's how the planet is discovered. That geometry, where we're in the equatorial plane of the planet orbit, and therefore we see the planet cross the face of its star, provides an interesting opportunity. So now imagine that that planet is not just a hard rocky body, but is a hard rocky body with a thin sheath of atmosphere. You can visualize that as the planet crosses the face of its star, there will be a little period of time when the starlight is filtering through the limb or the edge of that atmosphere as the planet crosses the star, and then again when it crosses the other side. If you then do spectroscopy of the star, that's providing, of course, most of the light, there will be an extra imprint of absorption when some tiny fraction of that starlight is filtering through the exoplanet atmosphere. So if that exoplanet atmosphere has oxygen or ozone or water vapor or carbon dioxide or carbon monoxide or anything, it will in principle imprint extra absorption. And the way you detect that is by the differential technique. You measure the spectrum of the star when the exoplanet is not in front of it, and you measure that very accurately. And then you measure the tiny difference it makes to the star spectrum when the exoplanet is just crossing the face of the star, causing a little extra absorption. That's the method. It requires extraordinary stability and has only been successfully done in space by Hubble Space Telescope and Spitzer with a slightly different method for about less than six exoplanets. Kepler 186f is definitely in the category of exoplanets where that technique is possible, but remember, Hubble is a small telescope, 2.2 meters. Spitzer is even smaller, less than about half a meter telescope. And these telescopes are really struggling to do this clever spectroscopic method on a star that's fairly faint, as Kepler 186f's parent star is. What we really need is either a bigger telescope in space, and that telescope will be the James Webb Space Telescope in a couple of years, or we need more nearby examples of Kepler 186f, a sort of Earth or super-Earth planet with a transit that we can then do this method on. And there are projects, of course, underway to find more nearby versions of Earths and super-Earths. So really, in a couple of years, I think these experiments will be possible. And they'll be extremely exciting because they could indeed be the first way we indirectly detect the presence of microbes somewhere else in the universe.
Okay, our next question is from Lisa. She asks, is it possible, theoretically, to use a gravitational lens to see a virtual image in front of the lens the way we can with optics? And if this is possible, would it be possible to then see a virtual image of the Earth with the implication that we would be seeing the Earth in prehistoric times?
Wow, that's a very interesting question. That's a high-level question, too, because it supposes gravitational lensing. So I'll back off slightly for the people listening to say what gravitational lensing is and then get to the nature of the question. Gravitational lensing is the situation where mass bends space and time as predicted by general relativity. And in the situation of gravitational lensing, you have a large mass, which in an extragalactic situation will be a massive galaxy or maybe the black hole at the center of that galaxy. And light from galaxies behind that large mass will be distorted or bent. In the case of perfect alignment, you actually have the background galaxy turned into a perfect so-called Einstein ring. And it's really analogous to geometric optics, only for gravity instead of for light. So in this image geometry, you have an object plane, which is the distant galaxy. You have a lens, which is the intervening galaxy causing the bending, and you have an image plane, which is where the Earth and the telescope is. Question is, could you have a virtual gravitational lensed image? And the simple answer is no, you can't, because the geometric optics does not quite work in the same way. I mean, there's reversibility of the optics, as in all traditional optic situations. The light path can be reversed. But there's no way to create a virtual image in terms of gravities acting on space-time. So the simple answer to the question is it's not possible because the actual optics equations for general relativity do deviate from simple geometric optics. And also, there's no way to alter the configuration of the situation. The only way we see lensing is if we're at the actual image plane. We don't have the ability to move in space and time and position ourselves at different situations. And if we were at a much different situation in the optical path, we wouldn't see the signature of lensing, and so we wouldn't be aware of its existence. But it's a very well posed question, very interesting question.
Okay, another question from Stanley. At a recent Steward Public evening lecture by Dr. Stark, he covered the cosmic dawn, or the time before the first stars, a threshold we can't currently observe. Will the indicator we have found be us no longer seeing visible or infrared light, or is there another marker?
Right, so for those of you, this is a question from someone local who went to one of our public evening lectures by one of our young faculty, one of our most recent hires, Dan Stark. He works on extragalactic astronomy, as I do. And he's talking about first light. And this is the notion that in a 13.8 billion year old universe, there was an early period of time, probably a few 100 million years, so a small fraction of the total age, where where the universe was still fairly warm and gravity had not yet had enough time to concentrate and collapse stars and galaxies. And if there are no stars, the issue of whether stars or galaxies form first is unresolved, but theory suggests that a generation of stars will form first and then coalesce into galaxies. But either way, there are no lights in the universe until the first stars form. And that time, that hypothetical time early in the universe before gravity has been able to form stars or galaxies, is called first light. And it is a huge goal of astronomy in the next decade to get as close to that as possible. It's not going to be, of course, possible to find the very first star in the universe or the very first galaxy. I think just for technical and practical reasons, that's unlikely. But the epoch of the first generally forming stars and galaxies should be identifiable. So at the moment, and in work by Dan and others, and he is a part of a very impressive team that have looked at the highest redshift galaxies, these galaxies are now at redshifts of about 10. The best confirmed redshifts are 10. There's some unconfirmed redshifts of 11 and 12. What does that mean? That means, alluding to the previous question about microwaves from the Big Bang, that means that radiation has stretched by a factor of 1 plus the redshift, or so stretched by a factor of 11 to 13 since it was emitted by that young star or galaxy. So that means in the oldest and earliest stars, galaxies that we can see in the universe now, with Hubble essentially, that light has been stretched by slightly more than an order of magnitude. And so the typical visual light from a galaxy has been shifted clear into the near infrared, beyond the level, beyond the wavelength the eyes can see. And so it is an infrared detection experiment. So both for Hubble's instruments and especially for James Webb's instruments, working in the infrared is where this work will be done. Because as far back as we've gone, these are not optically visible objects. There's no optical light to detect this long after the event, after so much redshift. It is an infrared detection experiment. That's hard because infrared detectors are not quite as perfect or as efficient or sensitive as our optical CCDs. So it just adds an extra degree of difficulty. But the infrared instruments are the ones that will look for first light. And they are doing a pretty good job with Hubble. Hubble has definitely used its last upgrade, its 5th servicing mission, with a very good infrared capability now, to infrared imaging capability at about 1 micron, to really push hard on first light. But James Webb was built for this job. And so James Webb will do the job fully and will essentially tell us when the first stars and galaxies form.
Okay, now Bob has a question. He saw a blurb from NASA about a star that was discovered in the Orion Nebula, and it was said to be only about 1 million years old. And so he's wondering, how can they age a star that new?
Yeah, good question. Because stars, even massive stars, live fairly long lives. The sun is 10 billion years, so if you could age date the sun to 1 million years, that would be 1 part in 10 to the 4, which is 100th of a percent, which is very precise. Now, the stars forming in Orion are more massive stars whose lifetimes may only be tens or hundreds of millions of years. So how can you age date a star? It's because the signatures of what happens in the first phase of a star's life are quite particular. The star forms in a very dense, obscured region, typically very dusty, and actually watching a star collapse or form out of gas for the first time is extremely difficult. People have seen hints of it happening. You need radio telescopes, far infrared telescopes. You can't do it optically at all because these are obscure regions. And also it happens very fast. The free fall phase for the collapse of a star by gravitational collapse is tens or even 100,000 years. Very short time indeed. After the star starts to form its first fusion reaction, it'll go through a little deuterium fusion before it kicks up the temperature enough to do hydrogen to helium fusion. It will then stabilize, but the initial intensity of the star is extremely strong compared to what it will settle down into. So there's a lot of UV radiation, and there's a lot of what we'll call a solar wind or a stellar wind coming off. And so many stars, many massive stars, when they form, go through what's called the T-Tauri phase, which is named after the prototype of this kind of object, which is the T, whatever number in the alphabet of the letter that is, the 20th or the 21st letter in the alphabet, that's the 21st brightest star in the constellation Taurus, so a very bright star. The T-Tauri phase is a very volatile, it's essentially the first era in which the star is stabilizing, settling down onto the main sequence to do its more steady routine fusion for the rest of its main sequence life. That T-Tauri phase lasts, depending on the mass of the star, between 1 and 10 million years. So in Orion, I think in this case, they identified a star massive enough, it's in its T-Tauri phase, and it's of the right mass that we know the T-Tauri phase is very short, probably 1 million or so years. And therefore, by seeing it in its T-Tauri phase, catching it in that volatile, very radiationally intense phase before it settles down into the boring main sequence, you can essentially peg it as being within about 1 million years of its formation. So that's generally how people age date stars. Nobody's yet really identified a star that is in the act of collapsing for the first time, because that happens very quickly in a very obscured place. But in that very first phase of a star, when it's just sort of settling down, if you like, but it's still very active and volatile and kicking out lots of UV radiation, that can be identified. And this is a case where that's been done.
Okay, another question from Stanley. What are some of the current applications of ALMA?
So ALMA is the Atacama Large Millimeter Array. It's one of the premier facilities in astronomy in this decade, the current decade. It's on the Chalandor Plateau in the northern Chile. It's a place I've never been, but I hope to go to actually next year. I've been to the other northern Chile sites, but not this one. It's just to mention the situation, because it's quite spectacular. It's at 5,200 meters in one of the driest parts of the world. Within 30 or 40 miles, there are places where there's not been rain in modern history, which is sort of in the last 130 years they've kept good records. So there are places where it hasn't rained for a century, incredibly dry, obviously incredibly high. And so for millimeter wave observing, where the water vapor in the Earth's atmosphere is an enemy, it completely absorbs, it's opaque, the Earth's atmosphere is opaque from the surface to millimeter waves, you've got to be as high as possible. Best of all, of course, is being in a balloon or a satellite or an Earth orbit. But the next best is to be in one of these incredibly high, dry places. And the ALMA array is probably in the best place on Earth you could make a millimeter array telescope. Obviously, very challenging to work there. I think astronomers, for the most part, will not be at the site of the telescopes when they observe. There's a base camp that's at a more reasonable altitude of a little over 3,000 meters, sort of where the base camp on Mauna Kea is. 5,000 meters, since most of us are not really fully metric, that's over 18,000 feet. That's Everspace Camp is a little higher than that, and that's a tough place to be. So observing there is very challenging, but it's an exquisite place to do radio astronomy. So ALMA is a very high-level international project. I forget exactly how many countries, but I think over a dozen. $1 billion plus project at this point. It's come through its commissioning phase and is doing routine science. I think it's in its second year of full science, with proposals from all over the world being accepted and oversubscribed. Maybe only 1 in 7 or 8 proposals. In first cycle, I think it was 1 in 15 proposals got time. Very competitive. So what is the science of a millimeter array telescope, and why do we want one? Well, it's an interferometer, so it's using widely separated radio dishes or millimeter dishes to synthesize a much larger aperture and thereby gain the angular resolution as if you had a telescope with the size of the largest separation between individual antennae. And in millimeter situation, this has never really been done before. The VLA and other radio telescopes do this kind of interferometry at centimeter wavelengths, but at millimeter and submillimeter wavelengths, it's never been done properly. And so ALMA is the first telescope to do this. It's a brand new capability. And so it's going to deliver both very high sensitivity, because there's a lot of dishes, and they're 15-meter dishes, and very high angular resolution, well under an arc second. I think 100th of an arc second is the best at the shortest wavelength it observes. And so these are both unprecedented capabilities. The science applications of ALMA are primarily involved in star formation and in drilling. Because of the transparency of dusty regions to millimeter waves, we can see right into Orion, to use an earlier example, the Orion Nebula, where stars are forming currently. You can see directly to the heart of these star forming regions and see on a very fine scale what's happening. So this telescope will deliver our first exquisitely sensitive and detailed maps of star forming regions relatively nearby, a few hundred light years away. Orion is further. Orion's over 1,000 light years away. That's one thing it'll do. The second thing it's already done, and there was a big press release a few months ago, is its image protoplanetary disks. These are also dusty regions, and where millimeter is a good place to observe. The star is still shrouded in dust, often in the case where planets are just forming, the star is barely switched on. And so there's already been some beautiful images from ALMA of the disk that forms around a very, very young star that has not yet formed planets. And that's a very exciting thing to do, because we know from our solar system that planets form very quickly. It only took 30 or so million years, that's out of a 5 billion year story so far, for all the planets to form out of dust grain sized particles. I mean, it was a very rapid process to build up planets. So if you can see protoplanetary disks in different stages of their formation, you obviously can't follow any particular one in real time, but if you observe a set of them and piece together the different evolutionary stages, you'll learn an enormous amount about how planets are formed. And now that we know planets are everywhere, 5,000 exoplanets known, that has become one of the most important questions. How do these planets form, and to give them the properties we observe when we detect them with Kepler and so on. So ALMA's going to do enormous and important work on planet formation, essentially. And then I'd say the final area that's more familiar to me, more like my research, that ALMA will contribute to, is the study of distant galaxies and their black holes. So black holes in distant galaxies, remember, a black hole lives in the heart of every galaxy, and often they're quiet or inactive, and also often they're shrouded in dust and gas and really very hard to see. So ALMA will see through to the heart of galaxies far away, billions of light years away, and be able to detect the activity caused by the black hole, if not the black hole itself. That's a little too hard to do for ALMA at those distances. And ALMA will also tell the story, it's telling the story of star formation nearby, but with its exquisite resolution. In distant galaxies, and in galaxies in general, it's going to tell the story of star formation in the universe over cosmic time. It's a very interesting story. What was the arc of star formation in galaxies? It appears to have peaked about 7 or 8, maybe 9 billion years ago. So the star formation history of the universe went through a crescendo as galaxies formed and stars were fiercely forming out of the gas in those galaxies. But it did go through its peak, and now we're on the quiet tail of star formation activity. Even though the Milky Way has some significant star formation, witness the Orion region, overall, in the aggregate, the universe has been through the heart of its star formation, and we're in the declining phase. But this whole story of over cosmic time of the star formation history and which kind of galaxies contribute the most stars when is a story that ALMA will help tell. And that was one of the reasons it was built.
Okay, our next question comes from Lisa. She asks, thinking about the universe like a balloon without an edge, massive objects deform the fabric of the surface. Does a black hole have infinite depth in its gravitational potential well? And does this mean that every black hole meets in the center of the balloon?
So it's a good analogy, the balloon analogy. Even astronomers who can be skeptical of analogies because they don't really follow the math very well. And in terms of gravity, we're really talking about general relativity, and that's how we truly understand the theory. The analogy, the curved space analogy works, the surface of a balloon, the distortion in it, in the sense of if you had a rubber sheet, or let's just imagine a flat rubber sheet, that's a little easier than going to the balloon, and you imagine masses on that rubber sheet, just heavy objects, and then you're rolling marbles or ball bearings or something across the sheet, those ball bearings or marbles will deviate in their trajectories according to the bent space-time, the curvature in the rubber sheet. And even if the math isn't exactly as general relativity would describe, the analogy is pretty good. You can see that the objects traveling through space-time across the rubber sheet, they don't really have any choice in the matter. They're just following the undulations, the curvatures of local space-time distorted by massive objects. So the analogy works pretty well for that. So we don't even have to go to the balloon thing, which is awkward because it's curved and it sits in 3 dimensions. Let's just stay with the infinite 2-dimensional rubber sheet. So what does a black hole represent in that analogy? In a sense, you're right. The black hole represents an infinite distortion of the rubber sheet. And I guess the 2 ways you can think about it, if you want to stay with the analogy, are that in the case of a black hole, some part of the rubber sheet is pinched down, is pulled down or distorted so intensely that it's essentially pinched off and becomes invisible from the rest of the universe, the rest of the rubber sheet. So that's one way to think of it, that is indeed what a black hole is. The event horizon marks a boundary of observability and an information membrane, sort of the limit to information. So think of the rubber sheet, really rather than just sort of tugged into a gently undulating depression, think of it as being extremely stretched vertically to be pinched off in some small region. That's a black hole. Now, the question alluding to an infinite distortion is actually correct, and that's because the black hole theory postulates a singularity, and that's essentially a problem of the theory now, because singularity represents infinite mass density, and that's not physical. So Stephen Hawking and others and all the gravity theorists who work on black holes understand that the current black hole theory is not the final theory, because the idea of a singularity within your theory tells you that you have a problem. The high energy physicists have a version of this problem, because in the standard model of particle physics, the electron has no extent. The electron is a point, literally a one-dimensional point particle in the standard model. And yet the electron has mass, and the electron has electric charge. And that means in the standard model of particle physics, the electron has infinite mass density and infinite charge density. Well, this has been known for decades, since the standard model was developed, and it's a problem in the theory. And in the standard model of particle physics, the theorists have just developed a little clever computational or theoretical techniques to finesse away the singularities or the infinities. It's almost become a standard trick if you're going to be a high energy physicist. In gravity theory, it's not as easy to finesse or get rid of these singularities. They represent a profound limitation of the current theory of gravity, and of course, by extension, of the theory of black holes. So I think, that's exciting, because it means that there's hundreds of theorists around the world that are working on new and better theories of black holes based, of course, on a situation where gravity is reconciled with quantum theory, as it would have to be in some eventual theory. And in that case, but at the moment, without such a theory to help us along the way, we are left with this idea of a singularity. And yes, as the question asked, that implies some infinite, mass density, some infinite distortion of space-time, which of course is slightly nonsensical. So that's just a problem we have of moving to a better theory.
Okay, we have a couple of questions about the James Webb Space Telescope. The first one is, what possible discoveries can we expect from James Webb? And the second one is, can you talk about the NIRCam that the University of Arizona is building for James Webb?
Sure. Discoveries are, of course, the gold standard. They're the secret sauce of any space mission. So you cannot sell and get a mission approved unless you say with some certainty things you're going to do and find. James Webb, with a price tag of over $8 billion, making it essentially, as it launches, the most expensive astronomy mission ever at the time of launch. Hubble, over its few decades, of course, has cost more, but at the time of launch, it didn't. So James Webb is the most expensive astronomy facility ever, bar none, ground-based or space-based. And so it had to be pitched based on science that everyone knew it could do. And those science areas, without any detail going into them, are, of course, exoplanet characterization, as I mentioned, first light, as I mentioned. So I've given the two biggest science goals of James Webb. And then the discovery potential is considered extraordinary. So how do you define that? How do you even play that out? Say you're just trying to get money for a facility. How do you even quantify something that's not quantifiable? In astronomy, what you do is you quantify it in terms of discovery space, in terms of the way the telescope operates. Because the history of astronomy says that every time you open up a new wavelength regime and or a new range of sensitivity or a new capability, a completely new capability, as in gravity waves, which LIGO is going to do for the first time and we haven't been able to do at all. So every time you open up a new capability in observation or instrumentation, you discover things you didn't predict or expect. And there's no reason to believe that James Webb, it won't be true for James Webb at all. And so even though you can't go to a hard-nosed congressional subcommittee funding your project and say what you're going to discover, that's just not how discoveries work. They're almost by definition surprising. You can say with very strong likelihood, based on a track record of 100 years or more, that astronomy facilities, when you add a new capability, lead to things you didn't expect and recast your view of the universe. In the case of James Webb, what you're doing is you're putting a 6.5-meter telescope in space. We've never had anything larger than Hubble in space. Hubble has an order of magnitude less collecting area. So you're increasing your sensitivity, your collecting area, by an order of magnitude, and you're delivering this very great sensitivity in the near infrared, in a wavelength regime where you've never had this sensitivity. So you really are in terrain that you haven't explored before. So people who work on James Webb are supremely confident that they will be surprised by things, that there will be discoveries. And the nature of discoveries is such that anyone can guess what they might be. Maybe we'll find new kinds of supermassive black holes behaving in different ways. Maybe we'll find new kinds of cataclysmic phenomena when stars die, like gamma ray bursts, but happening at longer wavelengths. Who knows? It's open for grabs. NIRCam, to answer the second part of the question, instrument out of from Marcia Riki's group in the Steward Observatory just down the hall from me, their lab down in the basement, is a multi-$100-million project. It was a very big grant to the University of Arizona over a number of years, and that is the prime camera on the James Webb Space Telescope. It has several imaging modes of different size pixels, different re-imaging optics to give you very high resolution. You could look, of course, very high resolution at a small area of sky, or lower angular resolution at a larger area of sky. So it has cameras to do that. And then it has a set of filters, I forget how many filters, but over a dozen, to isolate different parts of the infrared spectrum. Some of those filters are just broad filters, the equivalent of red, green, and blue for visible light. And some of those are very carefully chosen filters to center on spectral features redshifted to large redshifts, because James Webb is, of course, going to look for high redshift galaxies and their behavior. So there's some very strong emission lines in galaxies, like Lyman alpha, hydrogen line, that when they're redshifted into the infrared, you can isolate where you would expect that line to sit in a wavelength, and then take an image of the sky, and thereby objects who are emitting that line at that redshift will just pop out as detections. So NIRCam does that. It's a clever trick, but it's a trick astronomers have been doing for decades on the ground. NIRCam was delivered, I think, almost a year ago now, for integration into its instrument bay, and then the entire telescope, of course, will undergo integration, I think, late this year, or still a planned launch in 2016. And NIRCam is a great success. It passed all of its milestones. NASA, of course, has a contract to the U of A, this large contract, and they don't sign off on the contract and say they spend their money well until the instrument passes all its tests. It's called thermal vac testing, thermal vacuum. we're using large vacuum tanks at in Johnson Space Center in this case, though Kennedy has similar facilities. They put it in essentially a space environment, including the addition of cosmic rays and UV radiation to subject it to the harsh environment that it will face, in this case at a Lagrange point, 1.5 million kilometers from the Earth. And NIRCam performed flawlessly. So it's really just sitting there ready to be integrated into the telescope and go. Now Marcia's of course not, just relaxing and going to the beach now that she's delivered her instrument. Now is actually the fun part. Now she and her instrument team, who get guaranteed a few hundred hours of observing for their projects, that's part of the reward for building an instrument that the entire community will use. They're working out exactly what they want to observe with their time. So they're going to get, even while other people are using the telescope in its first year or so, the instrument team gets their own sequestered portion of time, and not insignificant amount of time, to do their science. And so Marcia and her team are busy figuring out what they want to observe with, and they only have a limited time to do this, and their data goes public just like everyone else's data. So if they don't do what they want with their data and publish it and get what the most out of it, then it becomes fair game for anyone to use. And that's sort of how astronomy works with big space facilities. It keeps everyone on their toes.
Okay, this next question might be our last question for the day. Comes from Ryan, and he asks, what exactly is magnitude and how is it measured? For example, if you were to query the SIMBAD database, you would be able to filter by a variety of magnitudes, V, U, B, etc. What are the differences between these, and what can they tell us about a star?
Okay, that's a very good basic astronomy question, but it's not a trivial astronomy question because it has a long history. So, and it's a subject of some consternation among other scientists because, to put it very simply, magnitude is the astronomer's brightness unit. It's the astronomer's own brightness unit that's particular to their subject. And in sort of the reason it annoys other people is it's based on a log 10 scale. So it's a logarithmic scale, and it's a scale where the larger number represents a fainter object. So it's a brightness scale that goes the opposite way to what you would expect, right? It's an inverse scale because the higher number is not a brighter object, it's a fainter object. And that drives introductory students and even some professionals slightly mad because it's a sort of not very sensible system. And it really is a historically based system. Magnitudes were essentially first, the concept of magnitudes has existed for almost 2,000 years. So Hipparchus in the 3rd century AD, I think, I don't want to get my dates wrong, but almost 2,000 years ago, put into place the compendium of astronomy of that era that survived through the medieval time and the Dark Ages as the book of astronomy called the Almagest. And that's from Arabic, of course, and it means the greatest. It was a 12-volume encyclopedia, and not many copies were made. And Ptolemy put in that all the knowledge of astronomy of the ancient times, including the Greek knowledge and the Roman knowledge and so on, and codified it as it would stay really for another 1,000 years until the beginning of the Renaissance. And in that compendium, he also codified the way astronomers would categorize stars. Now, remember, this is, of course, 1,000 years or more before telescopes, and almost 2,000 years before electronic detectors. So the detector for stars is the human eye. So the human eye is a logarithmic detector. That's why when which means its response is highly nonlinear. That's what lets the human eye see almost down to individual photons at night when you're dark adapted. Occasionally people can actually see individual flashes of photons, but human dark adaptation is quite amazing. And so the level of light you can see at night when you're dark adapted compared to the maximum level when you're looking into a bright light, don't ever look at the sun, but just imagine looking into a 100-watt light bulb from a distance of a foot or so. It almost hurts your eye, but your eye is not damaged. You can actually do that. That difference in intensity and photons is phenomenal. It's factors of trillions. And the only way the eye can do that is by being a logarithmic detector, having this nonlinear sensitivity. It's a feature, it's not a bug. It's great that we can do this. And so the eye is a logarithmic detector, and that sort of naturally meant that when humans were classifying the apparent brightness, how bright a star appeared to be in the sky, they were using a logarithmic scale. In other words, and this is exactly what Hipparchus and people at his time did, imagine you just go out into the night sky and you look at all the stars you can see. Now, just imagine, this is a long time ago, so it's easy to get to a dark sky where there are no city lights. You're seeing a really nice dark sky. And let's just imagine you stare at all the stars, and some are clearly brighter and fainter than the others, and just say you mentally, based on how they appear to your eye, you just want to divide them into groups, you know, the brightest, the faintest. Well, at Hipparchus's time, and in sort of common usage among astronomers at that time, they divided all the stars in the night sky, and it's from a dark place, it's over 3,000, into about 6 tiers or 6 divisions of brightness. And that was about as finely graded as they could do with the naked eye, because again, you have to agree with someone else about this. So if you take all the stars in the sky and say, I'm going to put them into 6 categories from the brightest to the faintest, 6 tiers or 6 brackets, you have to be able to agree on that. If you made them into 15 or 20 tiers, you probably couldn't agree on that because it's too fine. If you made it into the brightest half and the faintest half, that's too crude. So 6 tiers was what people did, and those were the 6 magnitudes, and they ranged from 0, the brightest star visible in the night sky, something like Vega, down to 6 magnitude, the faintest you could see, just barely visible to the naked eye. And so at the time of Hipparchus and Ptolemy, magnitudes were divided into those categories, where 0 was the brightest, it was an inverse scale, and it was a logarithmic scale, so the faintest was 6 magnitude, and below that the eye couldn't see. And astronomers essentially just took that scale and they kept using it, and then they extended it. So while the eye can only see down to 6th apparent magnitude, maybe a little fainter, 6.5, and individuals vary. Some of the range of visual acuity of humans is actually significant. So there are, apparently, I read in Sky and Telescope, there are amateur observers whose eyes can see 7th magnitude, and others could be out there with them staring at the sky, not seeing the stars they see. Now, of course, we use telescopes and detectors, but astronomers continue to use the magnitude scale. And of course, because we can now see so much fainter than the eye, that magnitude scale has been extended hugely. In magnitudes, 5 magnitudes corresponds to a factor of 100 in brightness, which means the difference in brightness between the brightest star you can see in the night sky at 0 and the faintest you can see at 6 is about a factor of 250 or 300. Now we can see with telescopes stars that are 20th, 25th magnitude. Hubble can even see 30th magnitude. So that if you do the magnitudes, that's 25 magnitudes fainter than the eye can see. And if every 5 magnitudes is a factor of 100, if you do the math, that's 5 factors of 100, which is 10 to the 10, which is 10 billion. So there is how Hubble can see 10 billion times fainter than the eye. And we're still using magnitudes, and astronomers still use them in their papers. But in many of their analyses of what they see in the sky, they convert into intensity units. And when they do physical calculations like luminosity and mass and other things that derive from luminosity, they always go into linear sensible units. So astronomers are stuck with magnitudes, baggage of astronomy. And I think some of my colleagues, many of my colleagues, and as a teacher, I don't like magnitudes because it's really hard and annoying for students to understand them. And there's really no reason to saddle students with the baggage of astronomers' history. But astronomers have strong sense of tradition because they like the history of their subject as well as the dynamic present of their subject. And so I think a lot of astronomers, and myself included, don't want to completely jettison magnitudes because it harks to this kind of amazing multi-millennium history of the subject. So I think that's going to do us for today, and that was good. I had some great questions, including some on topics we haven't covered so far in these live sessions. So we're back on track after the holidays. We'll be doing live sessions every couple of weeks, and we'll try and move the day around and the time around a bit to make it convenient for those of you in different time zones and different places. But thank you for participating, and meanwhile, we're working social media too. So even though the video lectures, don't change anymore. If you're just joining the course or if you've been with us for a while, stay part of astronomy and keep looking at the sky.